Hey guys, so I was tasked to go over just the Thevenin equivalent models for a circuit with a independent and a dependent source. So mainly the dependent source is what causes a good amount of issues sometimes. So just a friendly reminder, right? So the independent current sources, we always leave them open, right? We open them whenever they're present in the circuit, but whenever we're doing a Thevenin equivalent model. And then for independent voltage sources, we short them when we do the analysis. So here's a circuit. Let's just go over the circuit real quick. So we want to find a Thevenin equivalent model, right? We have a dependent source right here, and we have an independent source right here. And we know that this dependent source is dependent upon this IX that's flowing through this 3 ohm. And then we have ports A and B, which are typically connected to a external load, let's say. And so the point of doing a Thevenin equivalent, I don't know if they went over this in class, but the point of doing a Thevenin equivalent is to basically see what our input impedance looking this way is, and the equivalent voltage present at A and B. So then when we hook up a load, let's say this is our RL, when we hook up a load to our circuit, we're going to see it's going to be an easier circuit. It's just going to be a simple voltage divider because we already know what our Zn looking into our ports A, B is, as well as our voltage source present there. So just going over this circuit real quick, we first will want to find the R Thevenin. R Thevenin is, again, we want to see what the input impedance is looking into ports A and B. And so by doing so, we usually put like a V test. We put a test voltage source, and then we also say that the test voltage source has a current test going into the circuit, right? And then as we went over before, right, we always short this independent source. So we short this guy, then we still have this dependence on IX right here. We have this, this dependent current source that's dependent upon this IX going through this 3 ohms. And we still have this kind of test source that will help us find this input impedance. So again, this is just redrawing the circuit. We have a short circuit here. The 6 volts shorts out because we're doing a Thevenin equivalent. We still have this guy. Then we have that V test here. So just going through the KCL, you can see that we have this node right here, this 4 ohms. This is just V equals IR basically. And we have 2 currents going through it. We have I test going in this way, so we have I test here, and then we have IX here. And so they're going to sum up at this node. So we're going to have IX plus I test times 4 ohms is equal to V test. That's our equation 1. Now we can do KVL. Usually a good word of advice is that whenever we have a dependent source, KVL is usually the way to go. So we have a KVL at loop 1, which is this loop right here. We know that this guy is drawing IX. We know this guy is doing 1.5 IX. So we know that the equivalent going to the left right here is going to be 0.5 IX, just, simple mathematics. So we then know that at this loop right here, if we want to look at KVL, we have VX, which is basically, VX is basically across here because this is ground, this is VX. So VX is here is equal to 0.5 IX times 5 ohms. That's our KVL at loop 1. Now KVL at loop 2, which is this guy right here, is we have VX here, then we have IX times 3 ohms, and then we have the summation of those IX and I test times 4 ohms. So you can see that this is our KVL at loop 2. And then if we just take 2 and 3 together, because basically we have, I think we have 3 unknowns, but 2 of them we kind of want, right? We want V test and I test, because ideally we want to find our input impedance. And input impedance is going to be V test over I test is equal to R in a sense. You guys will just think about that a little bit. It'll work out in math. You guys will see it later. But just say that, let's say at this 2 and 3, we are going to combine these 2 equations. Then we have 3IX plus 4IX plus I test is equal to this guy right here, right? Because they're both equal to VX. And so it realized that this 4 times IX plus I test is basically our equation 1. So we can sub in V test here. And going through the math, we get minus 2 V test is equal to IX, right? And then let's say that we also want to plug this solution that we have here back into 1 because we want to find, basically we want, our end goal is to see V test over I test. So now we have a equation for IX. We want to find what I test could be. So you plug it in, you have minus 2 V test plus I test times 4 is equal to V test, right? Then if you do the math, you get V test over I test, which again is, this is our RN, right? V test over I test is our Rn is equal to 4/9, which is then our input impedance, if that makes sense. And then when you find the Thevenin voltage, that's our next part, right? After we find the Thevenin input impedance, we find the Thevenin voltage. And Thevenin voltage, we keep these two ports open. Then you leave this voltage source here. We don't short it anymore because we're looking at Thevenin voltage. Only short it when you are looking at the input impedance, or if it's an independent current source, you open it when you're looking at the Thevenin input impedance. So you do KVL on it. You have 6 volts is equal to -5 times 0.5 Ix, because again, we have 0.5 Ix flowing this way. And remember to define your polarity, right? Your current is going this way, so therefore your plus is here, your minus is here. So that's why your KVL is going 6 equals to -5 times 0.5 Ix plus 3 Ix, because that's the current flowing through here, plus 4 Ix, because this is 4, and then this is open circuit here. So Ix is going in this way, right? And then if you go through the math, you get 1.33 amps. And then if you look at your VTH is basically your output here, right? This is your VTH right here. Let's label this VTH for better clarity. So VTH is here is equal to Ix times 4 ohms is equal to 4.33. So your equivalent Thevenin model is going to be 4.33, which is this voltage source right here. And then your Zn, which is 0.44 bar. So 0.44 bar is your Zn. And then this helps because now, let's say we want to say, let's say we have a load of, this is going to be really ugly, but let's say it's going to be 1 ohm load, let's say, right? So now you know what this output voltage could be, right? Because you can just do a simple voltage divider. It's going to be 4.33 times 1 over 1 plus 0.44 bar, if that makes sense. And that's helpful because at first, this circuit is really complicated, right? If we make this our 1 ohm load, if I asked you, hey, what's my output impedance? You're going to have to, or what's my output voltage? Sorry. You will have to go through all the KCL, KVL, derive it, including this RL equals 1 ohm, find your output voltage, and then so on and so forth. But here we have a simple circuit. We can model it like this, and we can attach whatever load we want onto the output, and then we can get a certain V out. So yeah, that's how you find Thevenin output impedance and voltage based off of a dependent source, which is this 1.5 Ix. So yeah, let me know if there's any other questions. You can always shoot me an email at hgtam@usc.edu. So yeah, just let me know. Cool.